Welcome to AI Paper Slop. Today, we are tearing into a paper called Self-Supervised Visual On-Policy Distillation, or S2VOPD by Yijiang Li and colleagues.
Yeah, and for everyone listening who builds multimodal models, you already know the massive bottleneck we hit in on-policy distillation, right?
Exactly. You usually need this informative asymmetry. Like to train a better student model, you need a massively larger teacher model, or you need some kind of privileged information.
Right, like ground truth, bounding boxes, or verified reasoning traces.
Yeah, things the student just doesn't have. But this paper asks a brilliantly simple question. What if we don't have any privileged information at all?
And their solution is just a complete inversion of the standard paradigm. I mean, instead of giving the teacher model more information, they give the student less.
Which sounds crazy at first.
It does. They deliberately degrade and augment the image going into the student model, while an exponential moving average teacher, an EMA teacher, evaluates the original clean image.
So they're creating a highly effective training signal entirely for free. And the results are wild. A 4 billion parameter model, Quen 3.54b, gains 6.7% in average accuracy across fine-grained perception benchmarks using this.
That is a massive jump.
It is. It puts this tiny 4B model above massive models like Quen 3VL at 235 billion parameters. It even beats GPT 5.4.
Wow.
And uniquely, it improves both visual perception and mathematical reasoning. So for all the ML engineers and AI researchers listening, you know we are hitting a wall with human annotated data.
Oh, absolutely. Scaling up teachers is just getting too computationally expensive.
Right, and this paper provides a robust, compute-efficient way to push model performance without needing a stronger teacher or external rewards.
Well, before analyzing how S2VOPD achieves this, we really need to look at why this is a necessary breakthrough, specifically regarding the limitations of traditional on-policy distillation.
Or OPD. Yeah, let's get into that. So in standard OPD, you train a student on its own generated trajectories, right? And it receives this dense token-level supervision from a teacher model.
Right, which is generally preferred because it solves the train-inference mismatch you get with offline distillation.
Yeah.
You're correcting the student on the exact generative paths. It naturally tends to wander down.
But the bottleneck is that the teacher must have a distinct advantage.
Exactly. It needs to provide a better predictive target than the student can generate on its own.
Yeah.
And traditionally, we get that by scaling up to a massive compute-heavy teacher, which, costs a fortune.
Or we use on-policy self-distillation, OPSD, where the teacher and student share the same architecture and size, but we feed the teacher privileged info.
Yeah, we give it the reference solutions or the ground truth regions of interest.
But the issue for you, the listener trying to build the next generation of models, is that getting that privileged data is becoming incredibly difficult.
It really is. Model capabilities are starting to outpace the supervision that human annotators can reliably and cheaply provide at scale.
Yeah, we are basically running out of high-quality, dense annotations. It's like trying to teach someone chess.
Well, I like this.
Usually the teacher needs to be a grandmaster, or at least have a chess engine running in the background to point out the best moves. But this paper asks, what if the teacher and student are the exact same skill level, but the student is forced to play blindfolded?
What's fascinating here is that conceptual flip. It is a shift from additive asymmetry to subtractive asymmetry.
Subtractive asymmetry, I love that term.
Right. Additive asymmetry means giving the teacher a crutch, like extra data or extra parameters. Subtractive asymmetry means giving the student a handicap.
So the teacher and student share the exact same fundamental capabilities.
Yes. But their difference in available visual evidence induces a predictive discrepancy. And that discrepancy is what creates the asymmetry required for distillation. No ground truth annotations, no external rewards, no massive teacher cluster.
Okay, let's unpack this, because the implementation is where the training dynamics really take shape. How exactly are we achieving this subtractive asymmetry during the forward passes?
Well, it relies on a very specific routing of inputs. So we start with an image, which we'll call X, and a text question Q. We have our student policy, and we maintain an exponential moving average of that student's weights, which acts as our teacher.
Got it.
So the teacher observes the clean original image X. Meanwhile, we apply a stochastic transformation to create a corrupted view for the student. We'll call that corrupted view X-tiled.
So the student is looking at X-tiled, this degraded image, and it generates rollouts.
Right.
It predicts a sequence of tokens, building a trajectory based entirely on this bad view.
Exactly. The student samples multiple trajectories conditioned on the corrupted view and the question. Now, here is the critical step in the architecture. The teacher takes those exact same prefixes that the student just generated, but evaluates the next token distribution using the clean view, X.
Okay, I have to push back a bit here, because if I'm thinking about the latent space, this feels risky. If the student is looking at a highly distorted, noisy image, won't it just learn to generate garbage pathways?
That's a fair concern.
Like, if I'm blindfolded and bumping into walls and you're grading me on my wall bumping technique, I'm not really learning how to navigate the room, am I?
Building on your point about garbage pathways, that would happen if we were just doing standard reinforcement learning on the final output. But the nuance is in the objective function.
Oh, okay.
The student isn't being rewarded for the trajectory itself. It's being corrected at every single step along that trajectory by a teacher who can actually see the room. The training objective minimizes the generalized Jensen-Shannon divergence between the teacher and the student's next token distributions.
Ah, and that's calculated specifically over the teacher's top tokens, right?
Exactly.
So because the student is being scored against the teacher's distribution of the clean image, it can't rely on the blurry pixels. It's forced to pull from its own internal latent representations to overcome the visual degradation it's experiencing.
You nailed it. The gap between what the student guesses from the blurry image and what the teacher knows from the clean image is the learning signal. It's not learning to generate garbage, it's learning to reconstruct the truth despite the garbage.
Which brings us to a massive piece of this puzzle, the augmentation space. Because if the entire supervisory signal relies on visual degradation, how you degrade that image dictates the quality of the gradients, doesn't it?
It absolutely does, and the researchers conducted what is, to our knowledge, the first controlled large-scale search of the augmentation space specifically for on-policy distillation.
Yeah, they tested 4 main families of augmentation, right? First, there's information reduction, so things like downscaling, Gaussian blur, pixelation, or adding noise.
Right.
Second, geometric transformations like rotation, translation, and cropping. Third, photometric changes, adjusting brightness, contrast, or hue. And fourth, occlusion, so grid masking or randomly erasing patches of the image.
And their first major finding from this search is that asymmetry is absolutely mandatory.
Really? Mandatory?
Yeah, they tested a symmetric self-distillation baseline where both the teacher and the student just see the clean image with no augmentation at all. And that symmetric setup actually degraded the base model.
Wow.
Yeah, average accuracy dropped from 66.5% down to 65.2%.
I'd imagine that's because if there's no information gap, the distillation objective just becomes an echo chamber.
Exactly.
The teacher and student agree for the wrong reasons, and the model just amplifies its own confident errors instead of correcting them. But the moment they applied any single augmentation family to the student alone, performance improved.
Right. It proves you need a differential in the input to create a meaningful gradient. But their second finding is that the strength of the augmentation matters immensely.
It's not just a linear scale, right?
No, not at all. The performance doesn't just scale linearly with how much you mess up the image. It follows a distinct bell curve based on the teacher-student predictive gap.
And they measured this gap using the token-level Jensen-Shannon divergence during the early steps of training.
Yeah, so if the gap is too small, say a very light blur, there just isn't enough of a discrepancy to force the student to learn anything new. The latent representations aren't challenged.
Makes sense.
But if the gap is too large, like extreme pixelation, the student's input is too degraded to make any meaningful semantic connection to the teacher's clean image predictions.
It just falls apart.
Completely. The whole thing falls apart. They found a very specific sweet spot, a JS divergence of around 0.014, where performance absolutely peaks.
But even if you hit that perfect mathematical gap, the type of noise still matters. Finding 3 is that task consistency is king.
Yes. Let's explore why specific augmentations impact the latent space differently. If you apply a photometric change, like adjusting the brightness, you alter pixel values globally, but you aren't fundamentally removing structural information.
Right. The model doesn't have to infer missing details. It just has to look past a filter.
Exactly. Geometric changes, specifically cropping, present a totally different issue. Multimodal benchmark questions are often spatially grounded. If you use aggressive cropping, you might easily crop out the exact object the question is asking about.
Oh, right. So the teacher-student predictive gap becomes huge, far past our sweet spot, but it's entirely uninformative.
Yeah.
The student isn't learning to reason better. The question has simply become impossible to answer based on the available pixels.
Yeah. The paper showed cropping performance dropping down to 67.4% on strong crops. The augmentation must degrade the image while preserving the question-relevant evidence.
So information reduction techniques, on the other hand, force the model to actively reconstruct edges, shapes, and semantic meaning from partial data.
Exactly.
So what does this all mean? The paper outlines their best recipe, and the practical implications for ML engineers listening right now are incredible.
They really are.
The best configuration is downscaling the student view to 0.3 to 0.6x resolution and combining that with stochastic Gaussian noise applied 50% of the time.
Just think about the compute savings here.
Right. By downscaling the image, you are feeding significantly fewer visual tokens for the student to process. You are literally reducing your rollout and forward pass compute costs during training, and the resulting model comes out significantly smarter.
It's a rare case in deep learning, where a technique makes training cheaper and the model more capable simultaneously. But, rigorous engineers want to know why this specific recipe works so well under the hood.
Of course.
The ablation studies in this paper lay the mechanics of S2V OPD completely bare.
And the ablation results completely subverted my expectations, specifically around the teacher update rate.
Oh, yeah?
In a lot of EMA setups, tweaking the decay rate is this dark art that makes or breaks the run. For context, an EMA decay rate of 0.95 means the teacher is aggressively adapting to the student's new behaviors. A rate of Dre shear 0.999 means the teacher is sluggish, holding tightly onto past knowledge. Usually finding the exact right pace is critical to keeping the target stable. Yet they tested EMA decay rates from 0.95 all the way to 0.999, and the average accuracy barely budged.
It stayed within a 0.8% window. That extreme robustness is highly unusual.
It really is.
Normally, the pace at which the teacher updates from the student's weights drives the stability of the learning. But the fact that S2V OPD doesn't care much about the update rate suggests that the gradual evolution of the teacher is not the main driver of the performance gains.
And they proved that with the frozen teacher revelation.
This is my favorite part.
It's wild. They ran an ablation where they completely froze the teacher at the base model's initial weights. 0 EMA updates. The teacher never learns a single thing during the entire training run.
Yep.
And the model still achieved 75.95% accuracy. It recovered 93% of the total performance gain. Just think about the massive compute clusters currently being wasted on continuous teacher updating in standard labs.
This raises an important question, right? If the teacher isn't getting incrementally smarter, the learning signal must be generated entirely by the constructed view asymmetry.
It has to be.
The frozen teacher ablation is the definitive proof. The student is learning purely by being forced to map its degraded, low-resolution, noisy inputs back to the clean, confident distributions of the base model. The supervision is entirely in the recovery process itself.
That makes the divergence metric they use so much more important. They compared forward KL divergence, reverse KL divergence, and the Jensen-Shannon divergence, or JSD, and JSD won decisively.
It did.
Let's briefly define what KL divergence actually is for those who might need a refresher. Koldak-Leibler divergence is essentially a statistical measure of how one probability distribution differs from another.
Right.
In this case, it's measuring the distance between the student's next token predictions and the teacher's.
And how these divergence metrics penalize errors makes all the difference here. Forward KL is known to be coverage seeking.
Coverage seeking, right.
Yeah. When you minimize forward KL, you force the student to match all the probability mass assigned by the teacher. The problem is the teacher is looking at a high-resolution, clean image. So it might output probability distributions for fine-grained details that are literally impossible for the student to perceive in its downscaled view.
I'd imagine forcing the student to predict details it can't see would just lead to hallucination or severe model instability.
Exactly.
It's punishing the student for not knowing the unknowable. Does reverse KL have the same issue?
Well, reverse KL has the opposite problem. It's mode seeking. It encourages the student to find one safe, high-confidence mode and ignore the rest of the teacher's distribution. The student basically just zeroes in on the easiest, most obvious parts of the image and discards the softer, more nuanced corrective signals the teacher is providing about the harder-to-see elements.
So neither extreme works. How exactly does Jensen-Shannon divergence fix this?
JSD works by comparing both the teacher and the student to a mixture distribution. It's literally an average of their two distributions.
Okay.
Because it calculates the divergence symmetrically against this middle ground, it prevents the extreme penalties of forward KL and the tunnel vision of reverse KL. It effectively transfers the useful structural information from the teacher's distribution while avoiding excessive pressure on the student to perfectly imitate visual details it cannot access.
So the math is elegant and the training is cheaper, but do these blindfolded models actually survive in the wild when put up against 200 billion parameter giants?
Let's look at the numbers.
Yeah, let's look at the state-of-the-art results, and specifically the reasoning trade-off that plagues multimodal models.
The benchmark evaluation is really comprehensive. They trained S2VOPD on a 12,000 sample subset of fine vision using the Qwen 3.54B base model.
Just a 4B model.
Just a 4B model, and across 6 fine-grained perception benchmarks, so VBench, Zoom Bench, HR Bench, 4K, and 8K, and MME Real World, the average accuracy jumped from 70.7% to 77.4%.
Let me just contextualize that for a second. 77.4% on those benchmarks places this 4 billion parameter model above the Qwen 3 VL Instruct model that has 235 billion parameters. It beats GPT 5.4. It matches the 397 billion parameter version of Qwen 3.5. But here's where it gets really interesting, is how S2VOPD navigates the perception versus math reasoning dilemma.
Yes. Historically, in multimodal post-training, you basically have to choose what you want your model to be good at.
Right, the trade-off.
Prior methods that use privileged visual information, so methods like Vision OPD or ZWZ, which feed ground truth bounding boxes to the teacher, they get great perception scores.
Yeah.
But they severely damage the model's mathematical reasoning capabilities.
Right.
For instance, standard on-policy self-distillation drops math vision performance by over 9% at the 4B scale.
It's like cramming for a vision test by memorizing the eye chart.
That is a great way to put it.
When the teacher model is handed ground truth bounding boxes, it points directly at the answer. The student learns a shortcut. It learns to map specific question tokens directly to explicit visual cues provided by the bounding box, bypassing any abstract reasoning steps.
Yeah.
You might pass the vision test flawlessly because you know exactly where to look, but you haven't actually improved your brain's ability to process complex, novel information.
That analogy captures the latent space trade-off perfectly. Over-reliance on explicit localized cues prevents generalizable reasoning. Conversely, if you look at self-rewarding reinforcement learning methods like TTRL or Intuitor, those methods generally boost math reasoning, likely because they induce longer, more deliberative chain-of-thought responses. But they entirely fail to improve fine-grained visual perception because their optimization doesn't explicitly steer the model to look closer at the actual pixels.
And S2VOPD completely breaks this trade-off. Because it derives a perception-aligned signal from the model's own internal logic, rather than forcing external annotations or relying purely on text-based RL rewards. It boosts both domains simultaneously.
It's kind of having your cake and eating it too.
Yeah. At the 4B scale, it improves perception by 5.7%, and it improves math reasoning by 3.7%. It achieves near best perception performance while matching the strongest results on math reasoning.
When you force a model to reconstruct degraded inputs using its own latent representations, you aren't just memorizing visual features. You are forcing the model to engage in deeper, more robust structural reasoning to bridge the gap between the noise it sees and the clean distribution it needs to match.
And that underlying structural reasoning capacity clearly transfers over to mathematical problem solving.
Without a doubt.
It's a masterclass in extracting the absolute maximum value from existing model weights. You bypass the need for expensive human annotation, you bypass massive compute scaling for a giant teacher model, and you do it all just by strategically withholding information from the student.
It really represents a paradigm shift in self-supervised learning for large multimodal models. We spent so long trying to figure out how to give models more data, more parameters, more context.
Always more.
S2VOPD demonstrates that sometimes an intentionally restricted curriculum can build a much stronger foundation.
Which leaves us with a massive question for you to explore on your own. If subtracting visual information, like downscaling and adding noise, creates such a powerful self-supervised curriculum for vision language models, how could ML engineers apply this exact principle of subtractive asymmetry to other modalities?
Oh, that's a great thought.
Right. Could you intentionally degrade audio inputs, maybe apply severe frequency masking to force a speech model to build stronger semantic reasoning?
I could definitely see that.
Or what about video generation? Could you mask out random temporal frames, forcing the model to deduce the physics of the scene entirely for free, just to match the clean teacher distribution? The blueprint is right here.
It is.
That wraps up our coverage of S2V OPD. Make sure to check out our next deep dive on AI paper slop, where we'll keep tearing into the research, pushing the boundaries of machine learning.